Hello, welcome back to General Chemistry 1. My name is Daniel, and in this video we're going to be taking an introduction to organic chemistry. So that's probably a term you've heard before. Let's first define what exactly is organic chemistry. Organic chemistry is just the study of compounds that contain carbon. Any kind of carbon-containing compound is going to be an organic molecule. So carbon has a strong tendency to bond to itself and form very stable carbon-carbon bonds, either single, double, or triple bonds, as we'll see later in the video. So this allows for the formation of a wide variety of different compounds, all made up of this kind of carbon backbone with other elements or even perhaps more carbon going off of that backbone. We can see that down here. We see that there's biological molecules, there's ringed molecules, and then we also have on the right side here what are called hydrocarbons. Hydrocarbons are just compounds that contain both carbon and hydrogen only. And we're going to focus in on those for the first part of the video. So, when we're writing organic structures, there's a bit of a shorthand notation that we use. We're going to not draw out the hydrogens that are attached to each carbon in an organic molecule, but rather we're just going to denote the carbons as lines. So, for example, we see that here on the left we have the compound C6H14. Each of these carbons has a single bond to carbon, or two single bonds to carbon, and the rest of their octet is filled up with bonds to hydrogen. So that's the general nomenclature of an organic molecule, how it'll fill up its valence electron shell. We can write that out simply as this line on the right side. This denotes the exact same thing. So each of these points here is a carbon, and based on the number of bonds off of that carbon, there are some hydrogens. So this is what's known as a secondary carbon, so there's two hydrogens coming off it. A primary carbon is on the end, so that means that there's three hydrogens coming off of it. So you just need to be able to recognize this kind of shorthanded structure you see on the right side, and be able to identify the fact that there are hydrogens coming off it, even though they're not shown. So knowing that fact, we're going to get into the most simple organic molecules. Those are our hydrocarbons, just molecules with only carbon and hydrogen, nothing else. So the first kind we look at is the most very simple, and that's known as a saturated hydrocarbon, also known as an alkane. So an alkane is something that has a maximum ratio of hydrogen to carbon in any kind of hydrocarbon. So let me write that out and explain. So that means that it has the maximum number of hydrogens that you can place. So, there's 3 hydrogens over here. There's 2 hydrogens on each of these. And 3 hydrogens over here. Whereas, we'll get into this later, but an unsaturated hydrocarbon would be something with a double bond. If you have something with a double bond, carbon, there's 2 hydrogens coming off of that carbon. If it's a single bond carbon, then there's 3. So that's what I mean by saturated. This here is saturated because it has the most most hydrogen because of no double bonds or triple bonds. So basically, a saturated hydrocarbon is going to have no double or triple bonds, just single bonds. And they have a general formula CnH2n plus 2. So if we have something like C5, that would be H, 2 times 5 plus 2 is 12. And so on and so forth for any kind of alkane. So we can look at what's called straight chain alkanes. That means anything that's just like a straight chain, nothing coming off the branches, just a single backbone, the most simple organic structures. We see that they have their formulas over here, and they're named based on how many carbons they contain. So something containing 1 carbon has a prefix meth, and then the suffix ane. Something with 2 carbons has the prefix ef, and then ane at the end, and so on and so forth, depending on the number of carbons. So 3 would be prop, 4 would be bute, 5 would be pent, 6 would be hexane, and so on. You realistically should know the ones up to 9 or 10 or so. 9 is nonane. We also see that, obviously, as we increase the number of carbons, we're increasing the molar mass as well. And since these are all nonpolar compounds, since they're just straight chain hydrocarbons, they also have increasing boiling points as we add more carbons. So we see that the molar mass is increasing, the boiling point's increasing. That's just due to stronger London dispersion forces, like we talked about in the previous video. Okay, so that's just an important little thing to note. So we also have something known as structural isomerism. So let's say we have straight chain butane, which is on the left. What we can do is if we move one of these carbons over here, we get what's known as an isomer of butane. A structural isomer in particular is something that has the same chemical formula but a different arrangement of molecules. So each of these is C4H10, but you can see that in isobutane there is a carbon in the center here, whereas in straight chain butane it's all just a straight line of carbons. So what we'll need to be able to do is we're going to need to be able to identify structural isomers of a compound and also be able to recognize them and potentially even draw them out. So let's look at an example for pentane. So pentane we know is C5H12. So first off, the first one we can draw is obviously just straight chain pentane that has 1, 2, 3, 4, 5 carbons, like so. The second thing we can do is we can move this carbon up to here. So that would give us something like this. Okay, there we have our second structural isomer. So we see that instead now we have 1 and 2 carbons coming off of this same carbon over here. Now what's important to note is that this molecule is the same thing as this molecule. What do I mean by that? So if we counted up the carbons, we'd say, let's call this carbon 1, 2, 3, and 4. If we counted the opposite way, 1, 2, 3, and 4, we would see that in both of these, there's one carbon coming off of that second carbon in the backbone structure. So that means these two are equivalent structures. So they're not different isomers. Okay, so you could have drawn either one, it'd be equivalent. Okay, so then the final one would be if we took another of our group's carbons over here and also put it there. So that would give us the following. Okay, so we see that here we have a carbon just in the straight center. And then each of these is just a CH3. So we see that this also has the same kind of formula. So these are the 3 different structural isomers of pentane that we'll run into. And as we get more and more carbons in the structure, we're going to get more and more structural isomers. Once you get up to something like 9 carbons, you start getting a very large number of different isomers, more than you could realistically draw out at once. So you'll be pretty much limited to the structural isomers of maybe up to hexane or pentane, but we'll see more of that in the workshop. For now, let's get into the naming of alkanes. So in general, there's a very systemic process we can use to go determine the name of an alkane. The first thing we're going to do is we're going to identify the longest carbon chain. And that's going to be used as the basis for all of our kind of naming. So in this top example here, let's see, the longest carbon chain is going to be 1, 2, 3, 4. Then we could go down, say 5 and 6, or we could keep going and go 5, 6, 7. So this here, the one in red, is our longest chain. So we're going to use that as our numbering system. Next off, we're going to take the compound after it's been numbered, like so, and we're going to identify anything called side chains off of the backbone. A side chain is just a chain of carbons that's shorter than the main chain in red, and we're going to use those to we're going to identify